and we will be in what is called the Euclidean time formalism. There is a way of doing this calculation even in real time, but that is less explored, that is less developed. But the real time formalism will probably bypass some of these difficulties that you face in this way that I'm going to describe right now. The real time formalism was what was used in the original papers by Sorkin and company. This replica trick was introduced later by Wilczek. So let's consider a free field phi xt. So I'll talk about a scalar field theory, and consider a free scalar at time t equal to 0, and let's define the kets alpha as phi x acting on 0 on alpha is alpha as a function of x, like this. Then the vacuum wave functional, so phi, this is the field, this is the wave functional. So this is little phi, this is capital phi. This is the vacuum wave functional. It is defined as follows. It is the overlap of the vacuum with alpha, and it is up to some normalization 1 over square root of n, which won't play a role. It's the integral. It's a functional integral over all time minus infinity to 0. So this is the boundary condition that I'm imposing on the field. There's a functional integral d of phi, and then this is e to the power minus s, the Euclidean action. So that is the definition of the vacuum wave functional. And if you want to calculate the density matrix or the operator rho from this vacuum wave functional, what you do is, so alpha prime is equal to this object. So this is nothing but phi of alpha star, phi of alpha prime. And in order to compute this, and so this is the definition of this density operator. And suppose you want to trace over the degrees of freedom. Suppose.
Sorry, how to define vacuum?
Sorry.
How to define vacuum? Leo.
So this is the free field theory. So this vacuum is defined in the usual way where all the annihilation operators annihilate this vacuum. So this, so I'm talking about just free fields. Is that clear? So suppose you want to trace over degrees of freedom that live. So this is my entire space time. This I want to say trace over the degrees of freedom that live. Trace out the degrees of freedom that live in a certain region. So suppose we trace over degrees of freedom living outside some region B. Then what you do is you split your alpha in the following way. So alpha is equal to beta plus alpha b. So this is some function that is living in the region, and this is a function that is living outside the region. Similarly, alpha prime is beta plus alpha b prime, and then you sum over all this beta. So what you essentially do is you are gluing two copies of this copies of 1, and on the space on which alpha v lives. So what you get then is a reduced density matrix, rho of v, which is just a function of alpha v and alpha v prime. And this is an integral e beta of phi is a function of beta and alpha v star phi beta alpha v prime. So this is nothing but up to a normalization 1 over n out to be, you're putting boundary conditions now at t equal to 0 minus, so this is 0 minus, this is 0 plus, and you're putting boundary conditions for the field there, so phi of x 0 plus is alpha v, and then you're carrying on the functional integration. So that's what you do.
Sorry, where does the information of beta lie?
I'm sorry?
Where is the beta?
Oh, beta you're integrating over.
Right, in terms of the spatial,
So so these alphas that you define in this way,
right,
you're splitting them up into pieces that into functions that live only in region V and anything that is living outside region V.
outside the
Outside region
outside
V.
final
Yeah.
region.
Yeah.
So both alpha and alpha prime.
So they live in region V.
Same,
They live in the same space.
so they only differ within that final region.
Yes. Okay.
Finally, for the region 2, what kind of boundary conditions did you choose? I mean, I worry that if you break the region 2, you might have the situation where there is a discontinuity, for example, on the boundary, which usually, whereas usually we assume the
Right.
the
Yeah.
function.
So here we are
there is a
doing that.
concern that the factorization doesn't actually hold, strictly speaking.
Yeah. So here we are making assumption that suppose you're doing it over this space. So this is at t equal to 0, and then you're taking the two phi's and you're doing them over along this line.
Yes, so I guess I'm asking whether the value of phi from above and below, do you require them to be the same?
No. So what I've written here, this one is alpha v prime and this one is alpha v. So at this stage, they could be, they need not be the same.
I see. So
Yeah.
then you enlarge the Hilbert space already.
Yeah. But using this, what we're going to do next, so you remember that that we want to compute the entanglement entropy. So entanglement entropy, I told you that we don't know how to define log of rho, so we use that trick for the replica trick. And in the replica trick, we need to compute trace rho to the power n. So Sn was trace rho to the power n over n minus 1, and we need to compute trace rho to the n. So to construct rho to the n, you need to, now this is where this replication comes in. So to construct rho to the power n, you need to replicate n times and then identify the top and bottom branches. So you're computing, so you're making n copies of the same guys, but then the top object and the bottom object are the same. So n times, and you need to identify top and bottom branches. So what you have is a picture that like this. So you've got n copies of this picture, where each of these is supposed to correspond to rho, and then so you have n of these, and there is some angle that is phi that tells you on which branch you are on. So phi ranges from 0 to 2 pi n. So if it is 0, then you are on the first branch. If it is 2 pi, then you are on the second branch, and so on. And then you are supposed to identify this, the first and the last one. And this is supposed to give you rho to the power n. So because phi ranges from 0 to 2 pi n, what you have is an angular surplus of 2 pi n minus 1 in the space time, and that means that there is a conical deficit in your space time. So this means that there is a conical surplus in your space time. So this means that you need to know how to do quantum field theory in such space times, in backgrounds with quantum singularities. because of this conical singularity, this is the root for certain of the technical problems that we face in implementing this procedure for general field theories. Although for 1 plus 1 dimensional field theories, there are ways of making this more rigorous by what are called through a procedure which maps this problem to correlation functions of twist operators, which I won't have time to explain. Anyhow, so hopefully through this I gave you a flavor of how things could be computed in quantum field theories. And so you can imagine that to be able to do this calculation for an interacting quantum field theory will be very hard. And results for interacting quantum field theories are not available. Okay? Unless until.
Is that correct to say that the entanglement comes from the spatial derivative part in the action? Because naively, this is a free theory. How do you imagine that entanglement will localize on the boundary?
Yes. So you're So the reason so when I divide space-time up into two regions, the main contribution to the entanglement entropy corresponds to the short distance degrees of freedom that are living close to the boundary, and those are what give rise to the UV divergences that gives you the divergence in the area law. Okay, so if you want to think about these short distance divergences as arising because of the existence of derivatives, then yes. Okay. So what is known from the field theory side is that if you have conformal field theory, so conformal field theories are special kind of field theories with an enlarged symmetry. So this has got Poincare plus dilatation plus special conformal transformation. So if you have the special class of field theories, conformal field theories, then what is known is that for even dimensions, entanglement entropy will take on the following form. So D represents the space-time dimension, the total space-time dimension. So if you are in 1 plus 1 dimension, D is 2, and in this particular case, actually the leading term itself is a log term. But in generally, it begins off with some divergence that looks like this. So epsilon is a short distance cutoff, or it's a UV regulator. R is the size of the entangling surface, size of entangling surface. So by entangling surface, I mean that you're dividing up your space-time into two regions. But I've always been depicting it like this. I might as well depicted it like this. So this is what I mean by an entangling surface. And in odd dimensions, this behaves like epsilon p minus 2. There are no log terms in odd dimensions for conformal field theory. There is a constant, and plus there are subleading terms. So the coefficient of the log term is thought to be universal because this is independent of the regulator. Epsilon. So if you scale lambda epsilon to lambda epsilon, then this coefficient does not change. So you just put lambda, it just adds a constant piece. This coefficient is left the same. The same can be told in odd dimensions as well. Odd dimensions has a little bit of a subtlety, a little bit of a cheat that I'm happy to discuss later on. Is that clear? Okay. Any questions? So I'll pause for 2 minutes. Please ask questions, and then I'll move on to EDA safety. So till now, the story is, as I told you, that we are talking about entanglement entropy, and entanglement entropy was defined in a certain way. It's von Neumann entropy. The idea is that you're dividing space-time into two two regions, and then you're tracing out one of the regions. There are two things that I wanted to focus on. One of them was called one of them was this property called strong subadditivity, and the other thing was the positivity of the relative entropy S of rho sigma being bigger than or equal to 0. So these two keep in mind and be on the lookout for the analogous statements on the 8050 side. Okay. Yes.
So the definition for the entanglement entropy here is in free quantum field theory. So
For free quantum field.
yeah.
Yes.
So can it be generalized to?
Yeah, you would. So up till the point that I reached,
Mm-hmm.
that all that statement can be said to be. I mean, it can line by line. You can follow through for an interacting field theory as well.
Mm-hmm.
Where it differs is when you try to implement the boundary conditions. So I said that the top part and the bottom part need to be identified, and that for free field theories, if you work in the diagonalized space, so you can think of it as so there's some field that is living on. So this is phi 1, this is phi 2, and so on up to phi n. You can create a vector like that. And then you want to understand what kind of boundary conditions to put in. So this translates into a large matrix. That is, so the boundary conditions are implemented in that way and transforms into a large matrix that is acting on one that is living immediately before. Okay, and so this looks like a large matrix with a bunch of ones. But then what happens? Everything else is 0. But then what happens is this last entry is a 1 or a -1 depending, because you want to identify the field here with the field there. And then if you want to work in the diagonalized, if you diagonalize this, then the eigenvalues of this will work out to be e to the power 2 pi I k over n. So in the diagonalized representation, the boundary conditions look like twisted boundary conditions. Okay, but this particular statement I cannot make for an arbitrary theory. This particular statement I can only make for free field theory. Okay.
So maybe your function that later. Suppose that you are in automaton and it came to epsilon to say epsilon plus epsilon to power n or something like that, and then you can change the constant part.
No. What do you mean? Epsilon to
Epsilon plus epsilon square.
Epsilon plus epsilon square. But this is a dimension full quantity, so this does not. You won't be able to do this unless and until you put in another scale.
Okay,
but there's no.
So suppose that there are multiple scales, for example, and you can make some. There are many mass scales.
But then you've broken conformal invariance. Then the statement is different. So even for if you have a mass gap, then this statement even for even dimensions is no longer true. You get mass dependence in your form. So the statements that I made were just for conformal field.
Because that is good. I mean, you can extend 3D input to series, some 3D game series, people compute F localization.
Yes.
And then, so is that the universal quantum, for example? And the argument, I heard is that, for example, there is no renormalization, there is only some gravitational Simon stamp is normalized, only the imaginary part, so the real part here in this universal, etc. I'm not sure if you need to go through that argument before they have a good argument.
So I think the ambiguity that I'm talking about is not quite the same as what you're pointing out. It's just that it has to do with the fact. So suppose you were in since you asked this question. So in 2 + 1 dimensions, the leading term looks like that. Okay. But then you have a short distance cutoff. So suppose you are doing the calculation on a lattice. That means that the distance between two spaces you cannot resolve better than epsilon. Okay. So when I say that the numerator is L, actually this is uncertain by a quantity epsilon. Okay. So I can add plus some number that is not known to me times epsilon because it's uncertain. Okay. So it is through this. So when I expand this out, then what happens is that this constant piece gets shifted by this hash because of the fact that there's an uncertainty. So it is that uncertainty that may play a role. But then there's a way of removing this uncertainty by talking in terms of mutual information. So when you talk in terms of mutual information, that uncertainty goes. person about EDS-CTP in the audience, but this is just for the students, so let me talk about the EDS-CTP basics. And I'll talk about enough EDS-CTP that is needed for my lecture. So the statement is that under suitable approximations, a CFT in d dimensions can have an equivalent representation by a theory of gravity, or more precisely, it's a string theory. And again, there is a way of making this more precise. It's a theory of gravity in one higher dimensions, plus 1. So this is a conformal field theory. It has no gravity. It's living in d dimensions and it is equivalent to a theory of gravity that is living in d plus 1 dimensions. And a very well-known example is the duality between EDS5 and CFT4. So this gravity theory is a special theory. So it lives. It's a special background as well. The background for the gravity theory is what is called anti-de Sitter. This is a 5-dimensional anti-de Sitter space. And the field theory under question is a 4-dimensional field theory. I'm not going to make this statement more precise because I won't need it. But then the gravity side, the low energy effective action on the gravity side, LEA means it's a low energy effective action, can be written as 1 over 2 Planck length cubed. This is just dimensionality, d5x. And I'll be in Euclidean signature, so I'll write square root of g times the Einstein part plus a negative cosmological constant, which I will normalize like this. So there is a Planck length, and there is a length scale associated with the cosmological constant. So conventionally, this action is written as r minus 2 lambda. If you are very specific about signatures, if I was in Minkowski signature, then I would be in the mostly positive signature conventions. My conventions are the same as that involved. So lambda is negative, that's why I get a plus 12 over L squared. And you can verify that when you write down the equations of motion from this action, you get the following solution. So you get EDS5 as an exact solution to equations of motion, and it's an exact solution for an arbitrary theory of gravity with an arbitrary number of higher derivative corrections. EDS5 is an exact solution to an arbitrary theory of gravity with an arbitrary number of set of higher derivative corrections. What I mean by higher derivative corrections is that, as you know, that this this Einstein equation will get corrected. String theory gives us a framework for systematically computing the subleading terms to this action. Those are, there are two kinds, but then the kind of terms that I'm focusing on are what are called alpha prime corrections. So in principle, there are a set of alpha prime and G string corrections, and there could also be non-local corrections, but let me not talk about those. So alpha prime and G string corrections, and string theory gives us a framework for computing these corrections systematically. So for an example of a high derivative correction is something that looks like the square of the Riemann tensor. But of course, the Ricci scalar here is 2 derivatives. So just on dimensional analysis, this coefficient that is sitting in front of this Riemann square must be written like that, where lambda is a dimensionless coupling constant. And the way that this particular correction is associated with the 1 over n correction, or NF over NC correction in string theory. So anyway, so just be aware of the fact that EDS5 is an exact solution to an arbitrary theory of gravity with an arbitrary set of high derivative corrections. And the metric for EDS5 in what are called Poincare coordinates, that's all that I'll use for this lecture, can be written as L And because I was making the statement about an arbitrary theory of gravity, I'll put a riddle here. The length scale, or the ADS radius, this is called the ADS radius. So if I was in Einstein gravity, then in the conventions that I've written here, so this wouldn't be there. So this is what I mean by Einstein gravity. Then this L tilde would be the same as this capital L. For Einstein, gravity L tilde is the same as L, but it is different otherwise.
So without higher coverage operations, is the ADS still a stable solution?
What? Sorry?
Stable solution or not? Maybe you cut up a little bit around the thing.
So I know for a sphere there are all these claims that it is non-linearly unstable. So if you were working in global coordinates. For Poincare, I don't think there is an issue of stable. Is there? I mean,
I don't know. I mean, especially if you have higher coverage operations, I don't know.
Well, generally, you still have ghosts.
Okay.
yeah, but you can't take those
that
ghosts
is
seriously. But you can't take those ghosts seriously because you are in an effective theory. So the mass of the excitations are going to be like 1 over alpha prime. But then you're in an effective theory. You really can't take those ghosts seriously. You're supposed
So
to
it just goes beyond the
yeah.
regime period.
Okay. So in these coordinates, the thing to notice is that you've got flat space. Part of it is conformally flat. So dt squared plus dx1 squared plus dx2 squared plus dx3 squared. If I was in Minkowski, there would be a minus sign here, but I'm in Euclidean, so that's what it looks like. So this is the picture that this is your direction z. These are the coordinates of the metric that are living on tx1, x2, x3. So tx1, x2, x3 are the field theory directions. This is where the field theory lives. This is the ADS radius. The field theory now, where is the boundary? So the boundary is where the metric blows up. So z equal to 0 is the boundary. Or I'll put a small cutoff, z equal to epsilon. This epsilon will work out to be the same epsilon that appears here, or related to that same epsilon that appears here. So that is what the picture is. Okay. So this is the boundary theory. This is the bulk. The idea is that this boundary theory is supposed to be a complicated gauge theory with some large coupling constant. You won't be able to do perturbative calculations in this field theory. So the idea is that you will make use of this gauge gravity duality and extract information about the field theory using easier calculations in the bulk. Is the idea clear? Yes.
Going back to this question, it is true that you could have other phases, right, that have preferred entropically, lower free energy, right? We don't know the answer to this question. There's always the ideal solution, right? But there could be other phases, right? So that's, it's not obvious that you will see the instabilities linearly,
Yeah.
right? But we don't know whether ADS is a stable phase of the generic theory.
In a generic theory of gravity, yes, that's true.
So
you might have